Welcome to our power supply project walkthrough. In this video, we'll guide you through the process of building a power supply. Before we get into the schematic diagram, let's first take a moment to define what a power supply is.
Got electronics? Let's see how they turn wall power into gadget power. So, your phone, laptop, or gaming console, they all need power, right? But the power from your wall is AC, or alternating current. Your gadgets? They crave DC, or direct current. Here's the scoop on how we make that switch. First up, the transformer. Think of it like a bouncer at a club, stepping down the high voltage from the wall to a safer level. Next, the rectifier comes in. It's like a maze that only lets electricity go one way, turning that AC into a rough DC. But wait, there's more. The filter smooths out that rough DC, like a barista frothing your coffee to perfection. Finally, the regulator steps in, making sure your device gets a steady stream of power, no more, no less, and that's it. From AC to DC, all thanks to some nifty components. Pretty cool, huh?
We now have the schematic diagram for our AC to DC power supply project. This diagram illustrates the key components and their interconnections. The design includes 3 2-pin terminal blocks. Next are the 4 1N4007 diodes used in a bridge rectifier configuration to convert the AC input into DC output. Following that are the 3 resistors in the circuit. We then have our 3 capacitors, each rated at 1000 microfarad to smooth out and filter the pulsating DC from the rectifier and provide a steady DC output. Next are the 2 blue LEDs that will light up when the respective output voltages are being supplied by the power supply. Lastly are the LM7805 and the LM7809 voltage regulators, where the LM7805 regulates the output to a steady 5 volts, while the LM7809 provides a 9 volts output. Before moving on to the physical build, we first tested the design on a breadboard. This temporary non-permanent setup allowed us to assemble and evaluate the circuit, ensuring its functionality and identifying any issues. Testing on a breadboard confirmed that our power supply could deliver stable and accurate outputs across different loads. Next, we transitioned from the schematic diagram to the PCB layout. Using EasyEDA, we arranged the components and created traces for connectivity. After designing a PCB layout, we moved to the etching process. The layout was printed and a cover plate was cut to the appropriate size. Next, we ironed the printed layout onto the copper plate for over 20 minutes to ensure a proper transfer. Once ironed, we soaked the plate in water for 10 minutes and carefully peeled off the paper, leaving only the printed design on the copper surface. The copper plate was then submerged in ferric acid for over 20 minutes to etch away the unwanted copper. Afterward, we rinsed it in clean water to remove the acid, ensuring only the traces remained. Using acetone, we removed the ink from the traces, leaving a clean copper design. After etching, we drilled the copper plate to prepare mounting holes for the components. Once the PCB was ready, we began mounting the components. Each cover was placed carefully, from resistors and capacitors to voltage regulators. Every detail was double-checked. With the components securely in place on the PCB, we moved on to the soldering process. We paid close attention to the orientation of the components and the quality of each solder joint. This step required precision and patience, as proper soldering is crucial to the overall functionality and durability of the power supply. After completing the soldering, we inspected each joint thoroughly to confirm a clean and secure connection for every component. We then used a multimeter to be able to identify if there are any short circuits between the components. With the assembly complete, it was time for the moment of truth, the testing. We connected the PCB to the transformer and plugged it into the power source. To our excitement, the circuit powered up successfully and the LEDs lit up as expected. Using a multimeter, we measured the output voltages of each regulator, confirming that both delivered the correct values. The test results validated the design and assembly, marking a successful build. Finally, we presented our completed power supply to our instructor. During the demonstration, we measured the ripple voltage from peak to peak using an oscilloscope, where it showed that the 5 volts regulator had a ripple voltage peak to peak of 3.711 millivolts, while the 9 volts regulator had a ripple voltage from peak to peak of 2.539 millivolts, which successfully highlighted the results of this power supply project. Thank you for taking the time to watch our power supply project, and stay tuned for more.